From now on, we will study the dynamic stabilities of the aircraft. And so in lecture 7, we will look at the longitudinal dynamic stability. And in this first mini lecture, we will review the mass spring damper system, which is very useful for the analysis of different modes of longitudinal dynamics. So now let's review the dynamic stability of a mass spring system. And we're quite familiar with this kind of sketch. And we have a mass M is connected to the wall through a spring and also a damper. Okay, so now we have mass M and resistance due to position, which is K, and it's also called spring stiffness. And also for the damper, we have resistance due to velocity, which is indicated by C, and it's also called damping. Okay, so now we have the governing equation, and which is derived through the Newton's second law, and so I believe we're familiar with this. And it has actually two contributions. One is from the spring, which is a hook principle, and the second part is the from the damping. Okay, so if we reorganize it, and because A is second derivative of distance x, okay, so we have the governing equation. Now it's expressed by the unknown x, the displacement. Okay, so assume we have the solution in this form: x equals a times e to the power of lambda t. So if we put plug x into the governing equation, we have the governing equation becomes this. Okay, so we take the common part, which is a e lambda t, and then apparently we can have this quadratic equation: m lambda squared plus c lambda plus k equals 0. And naturally, now we can calculate lambda, which is actually from the formula we are quite familiar with. So through quadratic equation, we know lambda. If we rewrite it, it becomes this. Okay, so now I need to introduce another definition, which is called critical damping. And critical damping is the damping C, let the square root being 0. Okay, and physically the critical damping means there's no overshoot in the amplitude during the damping procedure. Okay, and so we can get C critical, that's critical damping, equals 2 square root mk. And if I introduce a plot here, it's easier for you to understand what is so-called critical damping, and it's indicated by the green curve. And apparently if you compare the green curve with respect to the red, or especially the red one, so we see there's overshoot, but for the green one there's no overshoot, and it's just approach towards the original or initial location. Just now we defined the critical damping, and now you may wonder if the damping is 0, which means that system we don't have the damper, and then the governing equation becomes, especially the left hand, becomes 2 terms, and then we call this a simple harmonic equation because there's no damping, and the system, the mass just carries on with this kind of sinusoid wave. Okay, and then based on the simple harmonic motion, we can define the natural frequency, which is omega n equals square root k divided by m. And then the critical damping, C critical, becomes twice m omega n. Okay, so let's move further. And people sometimes are more interested in the dimensionless damping, or the damping coefficient, which is denoted by Cauchy, and it equals and apparently it's a coefficient, it's a ratio, so it's a damping divided by the critical damping. And then we can have C, the damping equals twice the damping coefficient times M times the natural frequency. Okay, so now we have several definitions, and if we replace damping C and the stiffness K in the original governing equation for that spring mass damper system, so the governing equation becomes x second derivative plus twice cosine omega n times x first order derivative plus omega n natural frequency square times x equals 0. So the new governing equation, or the rewritten governing equation, relates with the natural frequency and the damping coefficient, which are very important for the dynamic analysis or stability analysis. So now we can rewrite the governing equation, which relates with damping coefficient and the natural frequency. And remember, we know x equals ae to the power of lambda t. And now let's consider whether we can replace lambda with cosine omega n. So we know lambda equals this relation, and then we know c, that's a damping and a natural frequency. Okay, so we just plug in c and a natural frequency, and we can know lambda equals minus damping coefficient times the natural frequency plus minus I omega n times square root 1 minus cosine square. So that's lambda. And so for now we can write down the solution x by using damping coefficient and the natural frequency. So it seems we have finished the derivation, or help you to remind you the derivation of the dynamics of the mass spring damper system. Okay, so now let's redefine the mu, and mu is the front part, the real part of lambda, and omega is the imaginary part of the lambda. Okay, so we have the definition, lambda equals minus cosine omega n, and we also have the omega equals omega n natural frequency times the square root 1 minus cosine square. Now let's do a bit discussion. If the mu is less than 0 or negative, which means this is a damped oscillation, and if you look at the x equals ae to the power of lambda t, and so the power is negative, and that which means that x becomes smaller, approaches to its original position, and then we have time to half amplitude, and only contrary if mu is positive. And if we go back to the expression of x, and the power of E is positive, which means the system is divergent, and then we should define the time to double amplitude because it's divergent. And anyway, so either t half or t double equals lambda longitude divided by the absolute value of mu. Either it's positive or negative, the denominator is positive. Okay, and then the period of time equals half 2 pi divided by the frequency. And what's the definition of frequency? How do you calculate frequency? Right, that is omega n times square root 1 minus cosine square. Okay, so now we complete the revision on the mass spring damper system, and you should know the several definitions and especially how to calculate the natural frequency and damping coefficient and the period, or the time to half amplitude or time to double amplitude. So this graph in the last slide helps you to understand the influence of Ksey in the damping coefficient. Let's first look at the Ksey equals 0 curve, and which is indicated by the black line, and this line corresponds to the critical damping, and we see already the position approaches to its original location. There's no overshoot, but with a decrease of damping, which means there's less damping in the system. So you can see there's more and more overshoots in the system with decreasing Ksey, and also that corresponds to a smaller period of time. Okay, so now it's end of the revision, and so in the next class we will study the longitudinal dynamics for the aircraft system.